All right, go and have your homework handouts out. If you would, please, just 3 problems for you to solve that use the 3 equations that we learned yesterday. Before we get into that, I do want to review some stuff we've been talking about recently, kind of leading up to these 3 equations. We talked about 2 methods by which we can transfer a charge from a charged body to a neutral body. What was one of those methods, Michael?
Conduction.
Conduction. And what was the method of transferring the charge through conduction?
Direct contact.
Direct contact. So the charged body touches the neutral body. Now, for the charge to actually transfer, this has to assume that the neutral body is not grounded, in fact. So the opposite of being grounded would be insulated. There we go. For the neutral body would have to be insulated. And when the charged body touches the insulated neutral body, what is going to happen?
They share a charge.
They share a charge, which means 2 things about that charge then. Since it's shared,
It's diffused.
or diluted, it's weakened, okay?
Diluted. And it's balanced.
One of you ladies help? It's the same charge. If it's shared, it's the same. So they're both negative or both positive. So it's a shared charge, meaning it's going to be the same charge for both objects, but it will also be diluted or weakened as it transfers. So the charged object will no longer be as strongly charged. The neutral body will not be as strongly charged as the formerly charged body was. The other method of charge transfer? Induction. And again, this requires the body to be insulated, but we would have to have some kind of wire going to the ground. So some kind of grounding wire or grounding mechanism present that can be removed later, right? But there has to be that ground wire or mechanism present. All right, so induction. How does it work?
It's not direct contact, but you're close.
Okay, the charged body is brought close to the neutral body, not touching. And what is the result of induction?
Opposite charge.
It's the opposite charge because a negatively charged body will drive electrons out and down the ground wire, resulting in a positive charge. A positively charged body will draw electrons up from the ground, resulting in a negative charge. So it's the opposite charge, and
Not shared.
so therefore it's going to be of equal strength. It's not going to be diluted at all. It'll be equal strength. However strongly positive this is, the other will become the same strength negative. Make sure you keep your eyes on your own paper. Equal strength. Yes, so induction. But for the charge to last, what has to happen? I've already referenced it. If you take the charged object away, then whatever negative was drawn up just goes back to the ground, or whatever negative was driven out just comes back up from the ground, unless the wire's cut or removed, or whatever grounding mechanism is present is taken away. Okay, so as long as that grounding mechanism is removed, the charge can last. All right, so there's our 2, conduction, induction. I want to make sure we keep those separate. We also talked about a device used to test the charge of an object. Kind of talk to me about the electroscope. We buy it, it's in the box. Hey, look at my electroscope. And I just go around testing charges, right? What do I have to do before I can test any charges?
You have to give it a known charge.
Give it a known charge, usually a very weak charge, but a known charge that'll cause what to happen inside the electroscope?
The leaves.
Move how? Michael?
Apart a little bit.
Apart just a little bit. You give it a charge, then the whole thing has the same charge. Therefore, just like the hairs of your head are separated from each other, the leaves of the electroscope will separate just a little bit if you give it that initial charge. Now I can take my electroscope and I can go around testing charges and just have a blast. When I test charges, of course, I want to be careful that I personally do not touch the knob. Because if I do, whatever charge was in that little electroscope goes into me. And now everything's neutral and we have nothing left. And we have to do it all over again. What do I do with the electroscope to test the charge?
You bring it near an object.
Bring it near an object. Don't actually touch the object, because again, that'll cause the charges to transfer and share. Now you don't know what you got. You place it near the suspected charge, and 3 things could happen with those leaves. The leaves could either spin further apart, they could come closer together, or they could just not move at all. What would each of those things indicate? Give me one of those things.
positive charge, then the leaves will move farther apart.
You're not wrong necessarily, because we usually assume an electroscope is given a slight positive charge. So in which case, yes, if it is another positive charge, the leaves will move further apart. But you realize you could have charged the electroscope with a negative, in which case that won't be the case. So the better way to say it is if it's the same charge as the electroscope, they'll move further apart. But again, we usually assume it's a positive charge for our electroscope. All right, so if it's the same charge, leaves move further apart. So then, Michael,
If it's the opposite, the leaves close in.
if it's opposite, which again usually would mean it's negative, then the leaves would move closer together. And then the last response of the leaves could be that they don't move, which simply means
It's neutral.
it's a neutrally charged, it's a neutral body, not a charged body at all. So again, as I'm looking here in the textbook and I'm seeing why you said what you said, when you're looking at a diagram, it shows leaves together for negative and further apart for positive. That's because we're assuming an initial positive charge. But it doesn't have to necessarily be that way. Yesterday we talked about this attraction and repulsion, and we demonstrated that attraction and repulsion is a force, right? And so a French scientist, Charles de Coulomb, came up with his law of electric force. Now, the fun part for students is there's the law of electric charges and there's the law of electric force. Michael, the law of electric charges states
Like charge that
is repel. Like charges, plural, repel. You have to have two charges. Like charges, repel.
Opposite charges attract.
There we go. All right, that's the law of electric charges. That tells you the behavior. What happens? Attraction, repulsion. Coulomb's law of electric force tells how strongly, with how much force do they attract or repel. So Coulomb's law of electric force is actually a formula. What was that formula? It's the first formula for this chapter that we need to know.
E.
F.
F. Okay.
And the law of electric force.
Okay. K. And then you have absolute values of Q1 and Q2 over R squared.
Good. Where the F is the force, that'll be measured in newtons. The Q, what does Q represent, class? The charges. Okay, that just represents the charges. By the way, what do we measure charge in? What unit? Coulombs, named after Charles de Coulomb. So we measured in coulombs. And then the distance. Now, unfortunately, the distance has to be expressed in meters because newtons require the use of meters. And so we've got to have the meters in there. Usually our distances won't be meters apart. So it'll have to go into moving the decimal from centimeters or millimeters or something. And then this K value. What was its numeric value? The constant of proportionality for electric force. Audrey?
8.999.
And the units we want,
Newtons.
we need to cancel away,
Meters squared.
and then we'll put a denominator to cancel away Coulomb squared. So 8.999 newtons times meter squared per Coulomb squared. Why absolute value? Why is that important, Michael?
Because electrons have negative charges and directions have weird negatives and positives too.
Yeah, if you have a negative charge and a negative charge, what will they do, class?
Positive.
They'll repel, which should give you a negative force, but mathematically negative and negative is positive. Two positives should also give a positive, but positives repel, which is a negative force. And opposite charges should attract, but if you have opposite signs, that gives you a negative, which would show repulsion. So everything's kind of backwards, so we just don't worry about it. We put the absolute value on there. This was our first equation we need to know for Coulomb's law of electric force. By the way, you don't have to know the number of electrons in a Coulomb or in a negative 1 Coulomb charge. Does anyone happen to remember?
6.242.
E18, yeah, huge number, 6.242 E18. That would be a good bonus question, though. But you don't actually have to know that number, just in case you're curious. Then we talked about this idea of as a charged body sits there, as it exists there, there is around the electrically charged body a region in which this electrically charged body could have an influence on other charged bodies near it. We call this area of electrical influence by an electrically charged body, what, Kendall?
Electric field.
An electric field. And the electric field has a certain amount of strength, largely dependent on how charged is the charged body. The greater the charge, the greater the electric field strength. Two ways in which we could measure it. The one way we said is simply take some small test charge, put it somewhere near the charged body, and literally measure the force. And that will tell you at that exact location what the electric field strength is. That was our first equation for electric field strength. Audrey, do you remember that equation?
E equals K.
That's the second equation. Anyone else? F over Q sub naught. You put a little test charge, you see how much force acts on it, bam, that's your electric field strength at that precise location at least. Well, big deal, you could put the test charge in a bazillion different places and get a whole lot of different readings, right? So that's not a particularly efficient way to do it. So a better way would be to say, well, we could actually then calculate for at any given distance, this is what the field strength would be. Obviously, we know that field strength will diminish the further away you get. And that gave us our second equation, which is what Audrey was trying to give us a second ago. E equals
K times absolute value of Q over R squared.
and you say that's the same thing as the force equation, right? Except the Q2, the second charge is the test charge, it canceled with this. The Q in question here is the actual charged body sitting there emanating out said electric field. And we can see how a greater strength of charge would produce a greater strength of electric field. We also see that as you increase that distance, the field strength will weaken. Now, what do we measure electric field strength in? And this equation is useful for seeing the units. Anyone?
Newtons per coulomb.
Newtons per coulomb. We have the newtons over coulomb. So newtons per coulomb will be our unit for electric field strength. Everything else kind of settles into place there. That's as far as we got yesterday. We did not quite finish everything I wanted to get in yesterday, but that's as far as we got. Questions on what we talked about the last couple of days? Let's look at the homework handout, then read that first problem for us if you would. And let's have Michael read the first one.
A particle with an electric charge of negative 5.73 E negative 6 coulombs is isolated in space. Determine the electric field strength that it is in sub 5 centimeters and 20 centimeters.
All right, it's asking for electric field strength, so I'm going to use one of my E equations, correct? Next, it actually tells me, and it asks at different distances. Which of my equations, class, will allow me to find electric field strength at varying distances?
Third one.
The third one. Electric field strength, distances. It's got to be that one. It can't be this one. Never mentions a force, never mentions what the test charge is. So we're going to go with this equation, and we'll say that electric field strength equals, again, we're going to assume the K slides up there to the numerator, right? That's standard algebra. And again, the K value, class mathematical value, and we'll just assume the units all work out and we get newtons per coulomb at the end. For the charge, what is the charge in question, Michael?
Negative 5.73 E negative 6.
And there's your coulombs. And then the distance, well, the first distance it asks for, class, is 5 centimeters. I'm going to have to change that to 5 meters, and then we're going to square all of that. All right, so we simply plug it into the calculator. 8.99 E9 times, well, you already did this, negative 5.73 E6, negative 6. And divide all of that by 0.05 squared. I just realized I plugged in a negative. Do I need to plug in the negative? No, you're taking the absolute value. Why would that be? Well, the electric field could be attractive or repulsive, right? As far as the electric field, if you get a positive charge that drifts into the electric field, it'd be like a tractor beam that sucks it in, right? Now you're in the Death Star, now you gotta figure out how to get out. Anyway, and if it's another negative charge, it'll be repelled by it, right? A la Vader, force shoving. Anyway, so we don't really need to plug in the negative, and I did just seeing it on the board. I'm going to put this in scientific notation because it's a very strong electric field at just a 5 centimeter difference or distance. What did you get for your first answer on the first problem, Michael?
2.06 E7.
That is 366, yes, 2.06 E7 newtons per coulomb. Ladies, did we get the same answer Michael had for the first part? I forgot to square. Okay, the next part of the problem, Audrey, go ahead and have you rework it, was at a distance of 20 centimeters. So class, we say 0.200 meters, or just 0.2 because I'm lazy. And what do we get for the electric field strength? If we go quadruple the distance outward, what do we end up with here, Kendall?
1.16.
think you might have forgotten to square. Audrey just redid it. What do you have, Audrey?
1 point,
Actually, no, hold on. Hayden, sit down.
1.29
There we go. That is the correct. Yeah, sorry, I can't let you walk right past other testers. Here, actually, I'll just give you the whole roll. Nice catch. Caught all the toilet paper, not the roll. All right. Anyway, I need to get more toilet paper for that. We have other students testing in the back of the room at the moment, so that's hence the distraction. Sorry, YouTube audience, adoring fans. Questions on this? Questions on this? All right. So make sure we don't forget to square. Look at the second problem here, and Kendall, read this for us.
Two positively charged particles are 10 centimeters apart if their charges are 9.31 e -6 and 4.58 -7 respectively. Find the force of repulsion between the particles.
All right, I missed all of that. Let's see here. We're finding a force of repulsion. We've got two charges and a distance. Okay, so what equation do we need to use for this, Kendall? The first one, Coulomb's law of electric force. And it says find the force of repulsion. So we are finding force. Now, it does mention force of repulsion. So right off the bat, I know I'm going to put what sign on my answer, class? I'm going to put a negative on my answer because this is a repulsive force. The negative isn't going to happen on its own, right? Because we're using absolute value. We have to affix the negative ourselves. All right, so in the top, of course, we have the 8.99 E9 again. It has two positive charges. So again, absolute value really doesn't make much of a difference since they're both positive anyway. The 9.31 E -6, the 4.58 E -7. And it says they're 10 centimeters apart. Hopefully we change that to meters, class. 0.1, and then we squared it. And then we plug all that in. It's almost a pound of force, actually. How much force do we get? Or excuse me, almost a pound of force for us U.S. people. Kendall?
-3.83
Good. Remember, it takes about 4 newtons to make a pound. This is just a little bit less than a pound's worth of force of repulsion. Which would be pretty cool to see. Anyway, how many got this answer? The -3.83? Other than maybe the negative? I saw a lot of you penciling in the negative. Audrey, question. What did you have for your answer?
I erased it, but it was really off.
It was really off, okay? Does it make sense now? Did you use the correct equation at least? So identified which equation you used, just a matter of putting it all in. Okay, questions? And the last problem, Audrey, read that for us.
Small sphere with a charge of 3.29 e -7 coulombs is attracted to a larger sphere by an electric force of 1.25 newtons. Determine the electric field strength of the larger sphere.
And again, when we say the electric field strength, it differs at every distance out. It's for this particular location of the small sphere. What's the electric field strength at that point? So what equation did we need to use here, Audrey?
The second.
The second one, the one we ain't used yet. And to determine the electric field strength, we simply divide the force, 1.25 newtons, by the charge, 3.29 e -7. And it is attracted, by the way. So that force, class, is a positive force. So for this particular object, it's a positive electric field in that it's attracting. We simply divide, and we get a pretty decent electric field strength. Audrey, what'd you have?
3.80
There we go, 3.80 newtons per coulomb. Questions on that one? Pretty easy equation to use, I would say. Questions at all? All right, set that aside if you would. If you would now turn to page 333 at the bottom of the page. Where we first looked at electric field strength correction, turn over to page 334. Page 334, and want to consider some things here with electric fields. Electricity and magnetism have a lot of overlap between them. We're not going to have time in this class simply because we're down to just a few weeks left with you. We're not going to have time to get into the chapter on magnetism. You studied that in pretty good depth in physical science already. It's not a hard thing to understand, not as much math that's involved with it anyway. But you remember playing with iron filings and maybe a transparency or a glass of some kind. You put the magnet and you see how the iron filings sort of form little trails, if you will, along what we call the lines of flux. Well, we have lines of force that we could see evidence if we did the same kind of thing, but with electrical wiring. And so you see the sketch there at the top of the page, or a little diagram of what it might look like if you had a wire loop running through an oil bath with little grass seeds floating on top. And we see that they would form lines of force between the two different objects. Lines of force exist between any two charged bodies, either repelling or attracting each other. There's 4 rules for lines of force that you see there in the second column of page 334. Do you see that numbered list, 1, 2, 3, 4? It says to map a particular electric field, you don't need to locate the lines of force by creating the field in a bath of seeds or fibers. Rather, you simply draw lines of force according to the following requirements. Read rule number 1 if you would, Audrey.
The direction of field strength is tangent to a line of force at every point.
All right, the direction in which the electric field operates, the direction of strength, is tangent to the lines of force. Number 2, Kendall.
The lines of force are perpendicular to every charged surface.
Good. Put a star next to that. The lines of force are perpendicular to charged surfaces. So, for instance, if you happen to have somehow an electrically charged box somehow, you wouldn't draw lines of force at an angle. You would draw lines of force perpendicular. Does that make sense? Now, obviously, here at the corner, the tangent plane would be this, and so now that one would go out, but otherwise, lines would be operating perpendicularly. That's important. It could go either in or out, and that's what we see in rule number 3, Michael.
The lines of force originate in a positively charged body and terminate in a negatively charged body.
There we go. That's interesting, because actually, truly, when charge moves, it is a flow of electrons, correct? So really, truly, electricity flows from a negative source to the positive source. There's this idea of electrical potential difference. That which has a great deal of electrons, that which has fewer electrons, there's a greater potential difference between the electrical charge here and this one here, and electrons always flow down to the positively charged body. Lines of force, though, are always drawn conventionally from the positive object to the negative. So as I've shown here, it looks like lines of force are coming out. That must mean this is a positively charged box. If I had a negatively charged sphere, we would draw lines of force coming inward. Now, notice, we said lines have to be drawn perpendicular. Let's circle. How would you draw perpendicular? Perpendicular to a tangent, right? On a curved surface, it's perpendicular to a tangent plane. But what did we learn in geometry is always perpendicular to a tangent? A radius. If I say you're in geometry, you better know the radius. So basically, as long as they go in line with radii, would this be in line with a radius? No. At that point, it should go in like that. So perpendicular has the idea of going along the radius toward the center of the circle. Perpendicular, if it happens to be a flat surface or something like that. They go into the negative, they go out of the positive. That's how we draw the lines of force, at least. And then rule number 4, Audrey.
The lines of force are distributed so that they are closer together. Where the field is stronger, the farther apart where the field is weaker.
Basically, if you draw more lines of force, it means it's stronger there. Okay, so if you have a really strong force, lots of lines of force close together. A weaker force, lines will get weaker further apart. This will happen naturally, though, along a curved body. As the lines spread outward, the force gets weaker. Picture Audrey's hair going outward, and it's more concentrated where the hairs are closer together and weaker further apart. Similar idea with the lines of force. As they happen to spread outward from a curved surface, you'll see them getting weaker. You see some sketches at the top of page 335 of what this might look like. If you had a positive and a negatively charged body, using those imaginary lines of force you might draw, we'll draw them coming outward from the positive body, inward to the negative body. And we can see that some of those lines of force then connect, which shows the attraction happening. Whereas if we were to draw 2 positive objects, both lines of force go outward, and when they would bump up against each other, they would push each other up and away, and we can see how the repulsion is demonstrated. Does that make sense with those first 2 figures? Mm-hmm. What about if you had flat surfaces? Well, let's draw it from the positive to the negative. We see the lines of force pretty close together. if we compare that with the next sketch where the lines of force are further apart, we assume then that the first picture, picture C, shows a stronger force of attraction than you would see in the final picture at the top of the page. Does that make sense? So just some things to know with lines of force. More of them and closer together where it's stronger. Always starting from the,
Negative.
that's what we would conventionally think. It's the opposite of what you would think. Drawn from the positive, going into the negative body. From the positive into the negative, always drawn what to each surface? Perpendicular to each surface. All right, questions at all on that? All right, well, I have a handout for you to complete, and we'll give you just a few minutes to work on this. Decided we're getting down toward the end of the year, and maybe we need to mix up the handouts just a little bit, so I put together a crossword puzzle for you. I like a crossword puzzle. You know how crossword puzzles work? Words up, down, across. See if you can do this without referring to your notes or book. Obviously, if you need to look them up, you can. Obviously, if you're watching on YouTube, the handout, the crossword puzzle's in the description of the video. But take a few minutes to complete the crossword puzzle, and then we'll go over it. It obviously doesn't look like the crossword puzzles in the newspaper. There's a lot more black space just because I'm not real good at putting them together, but you know, change of pace for you at least, right? finished. And Kendall, how many words left? Just a couple? All right. All right, let's go ahead and take a look at it and see if we can figure out those words that are evading Kendall at the moment. Let's start with one down, like charges, class. Repel. Let's go to two down. Device used for measuring the charge. It says measuring the charge. It really should say testing the charge of a body. It doesn't really measure it per se. Device used for testing the charge of a body, class. Electroscope. Number three, an uncharged body. Neutral. Let's see, four down, a negatively charged atom, anion, and then four across, opposite charges, attract. All right, at this point we've got a lot of 6 across already. Charge flows through a solid via delocalized electrons. Good. We'll take 5 down now using the C in attract. Number 5, a material that allows charge to flow easily. Conductor. We'll use the U in conductor to do number 7 across the SI unit for charge. Coulomb is correct. Let's see, we'll take the T in conductor to do number 8 across charge transfer in which the two bodies do not touch. Induction is correct. Let's go down now and take the S in electroscope and get 9 across, a non-moving charge. Static. Let's take the C in static, go 10 down, a flow of electric charge. Current. We'll use the R in current to help us with 13 across. An electric charge passing through a gas is seen as a spark. Let's see here. We also will use the N in current to help us a little bit with 15 across. Materials that do not allow charge to flow. Insulators. We can take the T in insulators to be a little bit of help, maybe with 12 down. Draw lines of 4s from, that's no help at all, from the positive body. Positive. Now, if you got it backward and said negative, it actually still fit, which means the T was no help because I'm the one who wrote the crossword puzzle, and you know, these things happen. Let's see. I never said this was one of my skills, okay? Let's see, I was just having fun on the computer. Let's see here. We'll take the S at the end of insulators, and there's a reason I went with the plural, to sort of not really help with 11 down. Really more the number of letters available would help here. Most of these allow charge to flow easily. Metals. Let's see, what are we missing? 14 down. The letter E represents electric field strength. And then we'll take the D from field and the E at the end from positive, or negative if you got it wrong. Take a 16 across, a sudden release of electric charge. Discharge. And that should take care of the crossword puzzle. Questions on that? All right, go and set that aside. You might save that to as a bit of a study guide for the test, or quiz, excuse me, coming up in our next lesson. For now, let's go ahead and take a look at another handout, which will help us practice with those 3 equations. All right, so 4 problems on this handout. and take just take about 5 minutes to work these 4 problems on this handout. Again, this handout's also in the description of the video. About 8 minutes remaining for your test, those in the back. We'll be finishing up in the next couple of minutes on that handout. Write the equation, plug in the numbers, type them into the calculator. All right, let's go and take a look at the handouts together. On the first one, find the force of repulsion between two negatively charged particles that are 7.5 centimeters apart if their charges are 6.4 e negative 7 coulombs and 8.2 e negative 6 coulombs, or microcoulombs. Assume they're in a vacuum. So what is our equation here, Michael?
F equals K times the absolute value of Q sub 1 times the absolute value of Q sub 2 over R squared.
All right, and so we plug in the 8.99 E9, we plug in the, now it says they're negatively charged, but we're taking absolute value anyway. So we plug in the 6.4 e negative 7, plug in the 8.2 e negative 6, divide all of that by 0.075 squared, and what do we get for our answer, Michael?
Negative 8.4 newtons.
Good, negative 8.387, blah, 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 or round it off, negative 8.4 newtons. Now the math didn't give you the negative. Why did you put the negative?
Because it's the force of repulsion.
Because it's a repulsive force. Negatively charged particles will repel, so negative 8.4 newtons. How do we do on that one, ladies? All right, Kendall, the next one. Two charged particles attract each other with a force of 12.3 newtons when they're 4.75 centimeters apart in a vacuum. One particle has a positive charge of 5.92 e negative 6 coulombs. Find the charge of the negatively charged particle. What equation should we use? The exact same one, except this time I'm solving not for the force, but for one of the Q's, one of the charges. I'm trying to get one of these by itself. So to get it by itself, what do I need to do here, Kendall? What's the thing that is, imagining this is in the numerator now, what is the thing that's least attached to the Q squared, to the Q sub 2? Well, the K and the Q are both being multiplied by, so they're actually right there with it technically. The R squared is underneath. How do I get rid of R squared? So we're going to say FR squared. That gets rid of this, and then I need to get rid of both the K and the Q by dividing them. So that's going to be our problem there. Does that make sense now? All right, so we'll plug in the 12.3 newtons. We'll multiply by 0.0475 squared. Divide that by the 8.989. Also divide that, I would divide separately, by the 5.92 e negative 6. And what do we get for the charge of the particle when we plug all that in? She's reworking it. Audrey, what did you have? Voice is out. All right, it sounds like I think you forgot to square the radius based on the number you started to say, Michael.
Negative 5.21 e negative 7 coulombs.
5.214 blah 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 e negative 7. Round it off, 5.21 e negative 7. We'll use coulombs for charge. But Michael's right, negative, because remember the two particles attracted. The one was positive. This has to have a negative charge. And of course it does say find the charge of the negatively charged particle. So again, we will put the negative because we know that's what the charge of the particle was. Ninth graders, you're dismissed. Let's take a look at the last two here very quickly before we head down. Metal sphere has a positive charge of 3.14 e negative 8 coulombs. It's placed a certain distance from a Van de Graaff generator. It's now attracted with a force of 17.5 newtons. Find the electric field strength of the generator at that distance. What equation did we need to use? Audrey, if you can kind of... E equals F over the Q sub naught. We know the force. We know the small test charge. We find the electric field strength. Does your voice have it in it?
5.57
And that is the correct answer there. Did we get that for the third problem? And for the last problem, an object with an electric charge of 7.93 microequivalents. Again, what's micro? E negative 6 hangs from a silk thread. What is the electric field strength of this object at a distance of 12.5 centimeters? What equation did we need, Michael?
E equals K times the absolute value of Q over R squared.
And so we plug in the 8.99 E9, we plug in the 7.93 E negative 6 coulombs. We divide all of that by 0.125 meters squared. And what do we get for that electric field strength, Michael?
4.56 E6 newtons per coulomb.
And that is correct. And you get that for the last one. All right, any questions as far as what to be prepared for the quiz, not test, the quiz coming up in our next lesson? All right, your only homework for the weekend is be ready for the quiz. Study over whatever you need to be ready for that quiz. No written homework this evening. All right, have a wonderful rest of your day, and you are dismissed.